After studying this module, you shall be able to know the concept of sequence and series and their types, learn the various tests of convergence and divergence of sequences and series, and apply the concept of sequences and series in economics.
A sequence is a list of numbers or objects arranged in a particular order. More specifically, it can be defined as a function whose domain is countable totally ordered set, such as the natural numbers n is equal to 1, 2, 3 and so on as shown, or the non-negative integers z greater than or equal to 0, 0, 1, 2, 3 and so on. In other words, a sequence is a list of numbers in a specific order. Now, like a set, it contains members, also called as elements or terms. The numbers of ordered elements can be finite, it can be infinite, and is called as the length of the sequence. Unlike a set, order matters, and exactly the same elements can appear multiple times at different positions in the sequence. We write sequence as an, where an is equal to fn, the nth term of the sequence, and n is a positive integer. For example, if an is equal to 1 by n, then a1 is equal to 1, a2 is equal to 1 by 2, and so on. Sequences can be finite or infinite. Finite sequences are sometimes known as strings or words, and infinite sequences are known as streams. Sequences are useful in a number of mathematical disciplines for studying functions, spaces, present-future value concepts, and other mathematical structures using the convergence properties of sequences. In particular, sequences are the basis for series, which are important in differential equations for analysis. Sequences are also of interest in their own right and can be studied as patterns or puzzles, such as the study of prime numbers. Sequences are written in a few different ways, all equivalent. A1, A2, A3, where A1 gives the first term, A2 gives the second, and so on. An, n from 1 till infinite, is where an is the nth term, and fn, n tending from 1 till infinity, where fn gives the nth term.
For example, the first four even numbers 2, 4, 6, 8 form a finite sequence. Similarly, an infinite sequence of all positive even numbers is written as 2, 4, 6, 8 and so on. Taking prime numbers in their natural order gives the infinite sequence 2, 3, 5, 7, 11, 13, 17 and so on. The Fibonacci numbers are the integer sequence whose elements are the sum of the previous two elements. The first two elements are either 0 and 1 or 1 and 1, so that the sequence is 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Example, the first 6 terms of the sequence an is equal to n square are 1, 4, 9, 16, 25, and 36.
Sequences can be arithmetic sequences or geometric sequences. Arithmetic sequence is where each term is obtained by adding a fixed number to the previous term, and geometric sequences where each term after the first term is obtained by multiplying the preceding term by a fixed number. The sequence 5, 7, 9, 11, 13 till 5 plus 2n minus 1, where each term after the first is obtained by adding 2 to the preceding term, is an example of an arithmetic sequence. The sequence 5, 10, 20, 40, 80 and till 5 2 to the power n minus 1, where each term after the first is obtained by multiplying the preceding term by 2, is an example of geometric sequence. In an arithmetic sequence where first term a and common difference d, the formula for the nth term is given by un is equal to a plus n minus 1 into d. In a geometric sequence with the first term a and common ratio as r, formula for the nth term is un is equal to a into r to the power n minus 1.
There are various types of sequences. Let us start with finite and infinite sequences. A sequence of a finite length n is also called an n-tuple. Finite sequences include the empty sequence that has no elements. Normally, the term infinite sequence refers to a sequence which is infinite in one direction and finite in the other. The sequence has a first element but no final element. A sequence that is infinite in both directions, it has neither a first nor a final element, is called a bifinite sequence, two-way infinite sequence, or doubly infinite sequence. Limiting behavior of an infinite sequence. Assume a sequence an is equal to n upon n plus 1, where n is a positive integer. Various numbers of this sequence can be written as 1 by 2, 2 by 3, 3 by 4, and so on, 100 by 101, so on, 1000 by 1001, and so on, for n is equal to 1, 2, 3, and so on. As n becomes larger and larger, successive terms become closer and closer to unity, but none of the terms is exactly equal to unity. This behavior is expressed by writing limit n tends to infinity n upon n plus 1 is equal to 1, where the symbol tends to imply very close or tending to, but not equal to.
A sequence is said to be monotonically increasing if each term is greater than or equal to one before it. For a sequence, this can be written as an less than equal to an plus 1 for all n belonging to capital N if each consecutive term is strictly greater than the previous term, then the sequence is called as strictly monotonically increasing sequence. A sequence is monotonically decreasing if each consecutive term is less than or equal to the previous one, and strictly monotonically decreasing if each term is strictly less than the previous. If a sequence is either increasing or decreasing, it is called a monotone sequence. An example for monotonically increasing would be a log function. Now let us study about bounded sequence. If the sequence of real numbers an is such that all the terms after a certain one are less than for some real number m, then the sequence is said to be bounded from above. In less words, this means that an less than equal to capital M for all n greater than n for some pair m and n. Any such m is called an upper bound. Likewise, if for some real small m, an is greater than equal to small m for all n greater than some n, then the sequence is bounded from below, and any such small m is called as the lower bound of the sequence. If a sequence is both bounded from above and bounded from below, then the sequence is said to be bounded. In economics, this type of sequences are generally used to depict business cycles, that is, the periods of booms and recessions.
A Cauchy sequence is a sequence whose elements become arbitrarily close to each other as the sequence progresses. More precisely, given any small positive distance, all but a finite number of elements of the sequence are less than that given distance from each other. The plot of a Cauchy sequence shown in blue as xn versus n, if the space containing the sequence is complete, the ultimate destination of this sequence, that is the limit, exists. A sequence that is not Cauchy, the elements of the sequence fail to get arbitrarily close to each other as the sequence progresses.
For sequences that can be written as n tending from 1 till infinity, with an belonging to capital R, we write an with the indexing set understood as n. Let an be a sequence. In other words, the sequence an is said to be converging if there exists a number capital L such that no matter how close we want the an to be to L, say epsilon close where epsilon is greater than 0, we can find a natural number capital N such that all terms an plus 1, an plus 2 and so on are further closer to capital L within epsilon of capital L. This is often written more compactly using symbols. For instance, for all epsilon greater than 0, there exists a natural number n such that L minus epsilon is less than an is less than L plus epsilon for all n greater than equal to capital N. In even more compact notation, for all epsilon greater than 0, there exists an n belonging to the set of natural numbers such that for all n greater than capital N, the absolute difference between an and L, that is, absolute an minus L, is less than epsilon. The difference in the definitions of convergence for one-sided sequence is complex analysis and metric spaces is that absolute value for an minus L is interpreted as the distance in the complex plane and the distance under the appropriate metric respectively.
An economic example of convergence would be the average fixed cost AFC curve, where the curve converges to 0 as output rises, never touches the axis. Let us briefly go through various tests of sequences. Ratio test. This is also known as D'Alembert's criterion. Suppose there exists R such that limit n tends to infinity mod an plus 1 upon an is equal to R. If R is less than 1, then the series converges absolutely. If R is greater than 1, then the series diverges. If R is equal to 1, the ratio test is inconclusive and the series may converge or diverge. Note: without the absolute sign, for R is less than 1, the series converges but not absolutely. Root test. This is also known as the nth root test or Cauchy's criterion. Define R as follows. R is equal to limit n tends to infinity supremum of n under root of mod an, where limit supremum denotes the limit superior, possibly infinity. If the limit exists, it is the same value. If R is less than 1, then the series converges. If R is greater than 1, then the series diverges. If R is equal to 1, the root test is inconclusive and the series may converge or diverge. Integral test. Let the function 1, infinity tends to real positive number be a positive and monotone decreasing and function such that fn is equal to an. If integral from 1 to infinity fx dx is equal to limit t tends to infinity, definite integral from t fx dx is less than infinity. Then the series converges. But if the integral diverges, then the series does so as well. In other words, the series an converges if and only if the integral converges. Direct comparison test. If the series summation of Bn where n goes from 1 to infinity is an absolutely convergent series and mod an less than equal to mod Bn for sufficiently large n, then the series summation of an where n goes from 1 to infinity also converges absolutely. Limit comparison test. If an, bn is greater than 0 and the limit n tends to infinity an by bn exists and is not 0, then summation of an where n goes from 1 to infinity converges if and only if summation of bn where n goes from 1 to infinity converges. Cauchy condensation test. Let an be a positive non-increasing sequence. Then the sum a is equal to summation of an, where n goes from 1 to infinity converges if and only if the sum A star is equal to summation of 2n A to n, where n goes from 0 to infinity converges. Moreover, if they converge, then A is less than or equal to A star is less than or equal to 2A holds. Abel's test, real analysis. Suppose the following statements are true. 1. Summation of an is a convergent series. 2. Bn is a monotone sequence. And 3. Bn is bounded. Then summation of a and bn is also convergent. Abel's uniform convergence test. Let Gn be a uniformly bounded sequence of real valued continuous functions on a set E such that Gn plus 1 x is less than or equal to Gnx for all x is an element of E and positive integers n, and let Fn be a sequence of real valued functions such that the series summation of Fnx converges uniformly on E. Then summation of Fn x Gnx converges uniformly on E. Dirichlet's test. The test states that if an is a sequence of real numbers and bn a sequence of complex numbers satisfying an is greater or equal to an plus 1 is greater than 0, limit n tends to infinity, an is equal to 0, mod summation of bn where n goes from 1 to n is less than or equal to m for every positive integer n where m is some constant, then the series summation of a and bn, where n goes from 1 to infinity, converges. Raabe-Duhamel's test. Let an greater than 0. Define bn is equal to n multiplied by an plus 1 minus 1. If L is equal to limit n tends to infinity, Bn exists, there are three possibilities. If L is greater than 1, the series converges. If L is less than 1, the series diverges. And if L is equal to 1, the test is inconclusive. An alternative formulation of this test is as follows. Let A and B a series of real numbers, then if b is greater than 1 and k a natural number exists such that mod an plus 1 by an is less than or equal to 1 minus b by n for all n greater than k, then the series an is convergent. Alternating series test. The alternating series test is a method used to prove that infinite series of terms converge. It was discovered by Gottfried Leibniz and is sometimes known as Leibniz test or the Leibniz criterion. Term test. In mathematics, the nth term test for divergence is a simple test for the divergence of an infinite series. If limit n tends to infinity an is not equal to 0, or if the limit does not exist, then summation of an, where n goes from 1 to infinity, diverges. A series is, informally speaking, the sum of the terms of a sequence. That is, adding the first n terms of a one-sided sequence forms the nth term of another sequence called a series. Thus, the n series of the sequence an results in another sequence Sn given by S1 is equal to A1, S2 is equal to A1 plus A2, S3 is equal to A1 plus A2 plus A3, Sn is equal to A1 plus A2 plus A3, and so on. We can also write the nth term of the series as S is equal to summation of an, where n goes from 1 to n. The series can be finite, that is, it has defined first and last terms, or infinite, that is, their last terms are not defined and they continue indefinitely. A geometric series is one where each successive term is produced by multiplying the previous term by a constant number called common ratio. One important use of geometric series is to find present discounted value. A series AN is said to converge or to be convergent when the sequence Sn of partial sums has a finite limit. If the limit of Sn is infinite or does not exist, the series is said to diverge. When the limit of partial sums exists, it is called the sum of the series. It can be written as summation of An, where n goes from 0 to infinity, is equal to limit n tends to infinity Sn is equal to limit n tends to infinity summation of An, where n goes from 0 to n. An arithmetic series is a series of numbers such that the difference between the consecutive terms is constant. For instance, the sequence 5, 7, 9, 11, 13, 15, and so on is an arithmetic progression with common difference of 2. If the initial term of an arithmetic progression is a1 and the common difference of successive numbers is d, then the nth term of the sequence an is given by an is equal to a1 plus n minus 1 multiplied by d, and in general an is equal to am plus n minus m multiplied by d. Let us now take an example to understand arithmetic series. The present value of the n installments of A1, A2, and so on, An, where the first amount has A1 has to be paid after 1 year, and the remaining amounts at intervals of 1 year, and with the interest rate P% per year, is given by An is equal to A1 by 1 plus R plus a2 by 1 plus r raised to the power 2 plus and so on, plus an by 1 plus r raised to power n is equal to summation I is equal to 1 to n ai by 1 plus r raised to power I, where r is equal to p by 100. When the annual payments are equal, that is A1 is equal to A2 is equal to and so on, is equal to AN is equal to A, then we have AN is equal to A by 1 plus R plus A by 1 plus R raised to power n is equal to A by R multiplied by 1 minus 1 by 1 plus R raised to power n, where R is equal to P by 100. Arithmetico-geometric series is a generalization of the geometric series which has coefficients of the common ratio equal to the terms in an arithmetic series. Example, 3 plus 5 upon 2 plus 7 upon 4 plus 9 upon 8 plus 11 upon 16 plus is the summation of 3 plus 2n by 2 raised to power n, where n goes from 0 to infinity. The harmonic series is the series 1 plus 1 upon 2 plus 1 upon 3 plus 1 upon 4 plus 1 upon 5 and so on is equal to the summation of 1 by n, where n goes from 1 to infinity. The harmonic series is divergent. An alternating series is a series where terms have alternate signs. For example, 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 plus 1 upon 5 minus and so on is equal to the summation of minus 1 raised to the power n plus 1, 1 by n, where n goes from 1 to infinity, is equal to limit 2. A telescoping series. Summation of bn minus bn plus 1, where n goes from 1 to infinity, converges if the sequence bn converges to a limit L as n goes to infinity. The value of the series is then b1 minus L. The p-series summation of 1 by n raised to power r, where n goes from 1 to infinity, converges if r is greater than 1 and diverges for r less than or equal to 1, which can be shown with the integral criterion as a function of r. The sum of this series is Raymond's zeta function.
Let us now summarize what we have learnt in this module. A sequence is a list of numbers written in a specific order, whereas a series is the sum of terms of a sequence. Finite sequence and series have a defined first and a last term, whereas infinite sequences and series continue indefinitely. There are various tests for convergence of sequences and series, such as the root test, integral test, ratio test, etc. Series are used for various economic purposes, for example, finding the present discounted value.